All right, so here's how the two models compare. On the left, you have the 7-layer OSI model, and on the right, you have the TCP/IP model. Notice the nasty part that the network layer is renamed Internet, where the IP addresses are. Transport layer is the same, and the top 3 layers are all just combined into an application layer, and the bottom 2 layers are combined into a network access layer. No particular importance to that, but there are both models, and some people use one model and some people use the other. All right, the internet layer is the same, IP version 4 or IP version 6 to use routing to find the physical location of the target, and the transport layer is the same, containing TCP and UDP. And the application layer is everything above that, reassembling the segments, decrypting them, and presenting them to the human user. So this process, these layers, the bottom 4 layers are in fact real and have addresses, and they have encapsulation. So you have like an envelope inside a bigger envelope inside a bigger envelope. That's what this encapsulation is. So at layer 4, if you are hit send on, say, an email client, it takes your email. At layer 4, it breaks it up into segments in TCP. Then it goes to layer 3 and takes each segment and packages it inside a packet with an IP address. And then it goes down to layer 2 and puts it in a frame with a MAC address. And then your network card sends it over your network as bits. And at the other end, it is opened up. The frame is opened up to reveal the packet inside, to reveal the segments inside, which are then passed up to the higher levels to become visible to the human. So here's a mnemonic for that, SPF10, like a sunblock, segment, packet, frame, and 1 and 0 for bits, if you like. TCP segments, IP packets, and Ethernet frames are the correct terms for these layers. So the other end is called decapsulation, where it takes the bits and converts them into a frame. Then it strips off the Ethernet header and turns it into an IP packet, and strips off the IP header and turns it into a TCP segment, and then takes the TCP segments and reconstructs them into a stream of data which can then be used by something higher level like a web browser. All right, so media access control is what MAC stands for. These are hardware addresses. They are flashed into the firmware of your network card, and they're supposedly unique for every network card, although all that really matters is that you're unique on a local area network. The first 24 bits determine the company that made it, and the next 24 bits are used to number each card that that company makes. All right, in IP version 6, they have this 64-bit system, but that's just part of the address in IPv6 that uses part of the MAC address. Anyway, IP version 4 is the most common IP layer. Most people see these addresses like this, 192.168.0.1. Most traffic still uses this older system on the internet. And so this is what it looks like. This is the official header. These are bits. So this is 4 bytes, 32 bits across, and 6 groups of 4 bytes down here. So you have the version, which is always 4 for IP version 4. And then you have time to live and source address and destination address. And so this labels the packet where it's going. A router can fragment a packet into smaller packets. Although this is not commonly done, it doesn't really matter that much. It turned out to be a pretty bad idea. It was invented a few decades ago to deal with token ring and Ethernet, and token ring is pretty much gone, so IP fragmentation is not something that serves any useful purpose anymore. And it was removed in IP version 6. The IP version 6 header is much bigger because the addresses are much bigger, but it's actually much simpler. Most of the other things are gone. There's nothing left but a hop count and a couple of other things. It tells you where it's going. If you have a modern computer running any modern operating system, they all support IP version 6 now, because the US government and the military will not buy anything that is not IPv6 compatible, and it's been that way since about 2010. So all modern devices are built that way so they can possibly sell to the government. And so this machine, you see, has an IP version 4 address here, 172.31.98.174, and it also has an IP version 6 address starting with FE80. IP version 6 addresses are in hexadecimal, and they're in groups of 4 characters, and there should be 8 groups of 4 characters, but if there's a whole region of 0, you can skip it and put 2 colons here to make it look shorter. Anyway, that's what the address looks like, a long string of hexadecimal. It contains 128 bits, 4 times as long as an IP version 4 address, and it's necessary because there are only 4 billion total IP version 4 addresses, and there are more than 4 billion devices on the internet, so they ran out of addresses. So the purpose of IP version 6 is to be a longer address so there's just more total numbers, so we can fit more devices on the internet. All right. All modern operating systems have IPv6 included by default, but many people don't understand it or how to secure it, so it can be used for forbidden activity like BitTorrent without necessarily being detected by your network monitoring or firewalls or such that aren't really IPv6 ready. So you might want to disable IPv6 if you're not using it. You can do it in your network card properties. So in the earliest days of the internet, everything was just determined, the network was determined by the first number, and the next 3 determined the device on the network. Then, because they never thought the internet would get very big, but that could only have a maximum of 256 total networks on the internet, and that didn't work, so they switched to this system until 1993, where there's class A, B, and C, and the first number told you what class you're in. The first half of the addresses are in class A, half of what's left is in class B, half of what's left is in class C, and class D and E hardly matter. And so that was the original plan, and so the class A is called /8 now. This is the new system CIDR because there are 8 bits that determine the network you're on, and the remaining bits determine the specific device. I see a question. Is there any performance benefit using IPv6 over IPv4? Not really. There were supposed to be, but what happened is the IPv6 rollout was so slow that all the good features are backported to IP version 4. So in practice, it doesn't matter. You won't notice anything. There are a few fancy features like mobile IPv6 and such, but in practice, you won't notice anything. Anyway, class B is /16. You have 16 bits to determine the network and 16 bits to determine the host on the network, so you have a maximum of about 65,000 possible hosts, and class C is the smallest and most common type of network, where you can only have 254 devices on the network. The first and last addresses are reserved for special purposes. All right, so City College has a class B address, 147, 144, and all the next 2 we can use to our heart's content. So, all right, and you can subnet in between these. We can have a /20 that's halfway between a class C and a class B. That's why they switched to this system. But you don't really have to know the details of subnetting for the CISSP level. That's something you need to know if you get Cisco certification. There are private addresses. You do need to know these. Anything starting with 10 is private, or 172.16 to 172.31, or 192.168. Those are all private addresses, and if you use them, those packets cannot go on to, you cannot send packets to these addresses over the internet. They will never get there because everybody reuses these addresses. You have to rent a real public address from your internet service provider, and you can only use these addresses locally, and they have to be translated to a real public address when they go off on the internet. All right, let's try this 4B that is now adjusted to be the right delay. Oh, and I should move it over a little. All right. Good. Looks like the network delay is under 10 seconds, which is pretty good. I guess that's it. All right, where do you find segments? All right, layer 4. All right, where do you find the 32-bit addresses? All right, that's IP version 4, 32 bits. All right, so what class is that address in? That's it. Class C is 192 through 223. All right, and where do you find the 48-bit addresses? All right, those are MAC addresses. Good. All right, let's see. All right, that's Judah. And VoIP, I know who that is. And Lua, I know who that is. Good. All right. So I think we can do one more. Let's do one more section of this. So, network address translation, I mentioned. This is where you have local addresses, like 192.168, and your router translates them to one or more public addresses. You normally use port address translation, so many local devices can all share one public address just to save money. Then their traffic is sent out on different ports. You can use static NAT, where you have one private address mapping to one public address, or something called pool NAT, but those are very exotic and I've never used them. So you'll have local addresses like 192.168, 101, 102, and 103, And then each device will have a default gateway going to the router, and the router has two network interfaces, one to go to the local network and one to go to the internet, and it will translate this so all these devices share this public address, 147.144, a real public address, and that you have to pay money for. You have to rent that from an internet service provider. All right, now when you try to send data off the internet, if I'm on here and I open a web browser and try to reach the internet, my local interface will decide I need to talk to 192.168.1.1, the default gateway, to get off of here. But you cannot send traffic to an IP address on a local area network because you're going to a hub or a switch these days, and this is Ethernet. You need a MAC address. So I know I need this IP address. I have to find the MAC address of that device to communicate with it, and you do that with ARP, Address Resolution Protocol. Every network is full of ARP packets asking, where is this IP address? Tell me, and the answer is the MAC address. You have to ask that question and get the answer before you can send packets to reach another device or to go off to the internet. There used to be something called reverse ARP, which is like Dhcp to give you addresses, not that commonly used. But this forward ARP is used all the time, and you'll see these packets anytime you run Wireshark on a network. So if I send a request, where is the gateway? I get a reply from the gateway. Now I know what MAC address to use. Now I can send packets to the gateway, which will then go off to the internet. The problem is, none of this stuff is encrypted. None of it is signed. There is no password. This was all designed in the early days of networking when nobody thought about security. So you can easily poison the ARP. An attacker in a coffee house can just listen to the ARP requests and then send false replies. And if they get there first, this device will just believe them, so I can lie and tell it I am the gateway. Then this client will send all the traffic to me, and I can forward it, and it will go to Facebook, and I can modify it. So I could inspect it or steal the contents or alter the contents if I'm in the middle here, unless you're using an encrypted protocol like HTTPS, in which case I can get in the middle and I can see the traffic, but I can't modify it or read it because it's encrypted with a key I don't have. That's ARP poisoning. All right, so unicast is where you have one sender going to one receiver, which is what almost everything is on the internet. There is multicast, one sender going to several receivers used by routers, but not by much of anything else on the modern internet. And then there's broadcast, which is used anytime you don't know who's out there. A lot of those ARP packets are broadcast, DHCP requests are broadcast, so you send them to a IP address of 255.255.255.255 and a MAC address of all Fs, and that is something that goes to every device I can reach. It's just like yelling in a room. Like, I don't know what's going on, somebody help me. With a question like, I just turned my computer on, I need a MAC address. Is somebody out, an IP address, is somebody out there a DHCP server? So these are local broadcasts. There used to be something called a directed broadcast that you could transmit over the internet, and it would then perform a broadcast at the other end, but that turned out to facilitate denial of service attacks using Smurf attacks, so that's been blocked for decades, and you can't do that anymore on the internet. You can, a normal NIC, a network interface card, might sometimes see packets that are not intended for your card if you're using hubs or wireless networks. But your network interface card will check the MAC address, and it will not pass any data into your machine that is not addressed to you. But NICs can be set in promiscuous mode, so they will skip that check, and you will now listen to traffic that is not directed to you. There is no normal reason to do this. It normally means that you're an attacker, or you might be a network engineer trying to diagnose a problem. That's why Microsoft has made a bunch of protocols to detect promiscuous NICs and report them as possible security risks. Anyway, that's your NIC in your network card in promiscuous mode. All right, and you have to have root privileges to do that. Switches direct traffic at the MAC address, so if you're on a switch network, usually no traffic arrives at your Ethernet card except traffic that's directed at you anyway. So promiscuous mode doesn't really do anything, but it does work on an unencrypted wireless network, because there's no way to stop wireless packets from reaching every device in the room. All right, so here's TCP. It has source port and destination port, sequence number, and acknowledgement number used to reorder the packets. And it has these flags like SYN and ACK and other things that we don't really have to worry about too much here. So the first 1,024 ports are called well-known ports, and they are for important services like HTTP and HTTPS, so you can only listen on them with root permissions. They're reserved for these special common protocols. All the rest are used for less important things like games and temporary ends of connections, so you do not need root privileges to listen on those ports. A socket is a virtual cable between one program and another program, and it consists of these four numbers. You have a source address and a source port, a destination address and a destination port. And now those two processes, one on my client and one on the server, can send data back and forth without it getting mixed up with anybody else's data. That's why they call it a socket. It just sorts the traffic so this process can talk to that process back and forth. And you need all four numbers to define that socket. So there is a state of a socket. You can be listening, waiting for SYN. Yeah, WebSocket. Yeah, I think that's what they call WebSockets. What happens if you don't obey the ports? If you want to transmit HTTP? Oh, if you, what happens is you can use non-standard ports if you want to. All that happens is if I was to put my web page on a non-standard port, then you wouldn't be able to load it this way. You'd have to put a colon at the end, like 8080. And then you could load a page from a non-standard port. That's all. But if you do, then it's more inconvenient for people. So if I ran my web server on 8080, you would have to add that in the URL. And you can put any service on any port, but if you do, then it will be irritating for people to connect. And a lot of people will not be able to connect as easily. That's all. But there's nothing particular happens about it, except it confuses everybody. It's kind of like you could wire your house so the red wire was ground and the white wire was hot if you wanted to, but it would confuse people and sooner or later they'd make a mistake. Anyway, so yeah. All right, so you can have your network connection can be in a state. It's listening, means it's waiting for someone to connect. Established means you completed the handshake and now you have a socket with the other end connected. And that's what goes on during the handshake. The handshake uses these TCP flags, and I think it's coming up. Yeah, here's the handshake. I send a SYN, the server sends a SYN ACK, and I send an ACK. That's the TCP handshake, those three packets. And after you do that, you now have an established connection, so you can send traffic back and forth. The other ones here are push and reset to close a connection, fin to finish a connection normally, and push and urgent that don't matter that much. There's a few other flags that I've hardly ever used. Those are the TCP flags. And that's all there because TCP is a connection, uses connections. Follow up, so while scanning for malicious packets, do we have to listen on all ports for all protocols? Well, your best firewalls will in fact do that. Most people leave things on the normal port, but BitTorrent, for example, moves to any port it can use and tries to hide, and a lot of malicious traffic tries to hide. So a modern firewall, like a Palo Alto firewall, is very smart, and it will inspect the traffic. It will do deep packet inspection and look at the structure of the packet, so it will not be restricted to assuming it's on the right port. So yeah, it's a question of how smart your devices are. It is a common security feature to move your stuff to a different port. For example, if you have an SSH server and you move it to a non-port, move it off port 22, you'll get a lot less attacks. There's a lot of bots that are trying to log into everybody's server on port 22. And that's why a lot of people say just move it off port 22 and you'll have much less attacks. If you put a VPN, I think my student in my lab set up a VPN server. and listened on a standard port, and within 30 seconds, you got a whole bunch of connections of people in China trying to surf porn through it. And when we moved it to an unexpected port, that did not happen. So a lot of people are just scanning the expected ports and not looking on the funny ports. So you will spare yourself a certain amount of background chatter if you use a non-standard port, but it will also mean that all of your staff will have a hard time using it because they won't remember what port to connect on. So, it's inconvenient. So almost everybody just uses the standard port anyway, just to make life simpler. And then there's UDP. UDP has a very simple header. All it has is a source port and a destination port, and nothing else really. It doesn't have any handshake. It doesn't have any SYN and ACK. It doesn't have any sequence number because it does not make sure the other end is listening first. It does not detect an error and retransmit it. It does not rearrange the packets to put them in order. It just spits out data and you receive it or not at the other end. So this is what you use for like a security camera that's just constantly spitting out an image and you don't know or care whether anybody's really watching. It's faster and simpler, but not reliable. All right. So let's take a look at 4C, and I think that's enough for today. Oh, and I have to make it longer. Although last time it was so short that I think I could possibly have gotten away with 30 seconds, but I think I better turn it up for a minute. If everybody answers the question, it stops anyway. So you don't really have to wait a whole minute. It just waits until everybody answers, which is kind of polite. The only real use of this time is in case somebody doesn't answer at all. All right, 4C is here. All right, looks like that's it. Oh, this over a little. All right. All right, what kind of transmission uses that address? Yeah, the delay is down to about 8 seconds, about as good as it gets. Yep, that's broadcast. Just reaches everybody in range. All right, what ports require administrative privileges? Yep, one's below 1024, possibly including port 0. I'm not sure if port 0 is valid or not. Anyway, I've never seen it used. All right, what flag initiates a connection? SYN. Yep, SYN SENAC AC. All right. And what UDP flag initiates a connection? Yep, that's it. Can't fool you people. There are no flags and no connections in UDP. All right, that's VoIP. I know who VoIP is. I'll have to figure out who ASD is. They'll probably have to tell me. I don't think I know that one, if they care about points. All right, good. Well, I'm going to stop the recording.